Our final speaker for this session is Anish Mudaraddi, and he'll be talking to us about Muon Galaxy, facilitating fair data analysis in muon science.
Hello, everyone. Welcome and thanks for coming. My name is Anish, and I'll be presenting my team's work, the Muon Spectroscopy Computational Project. We're presenting Muon Galaxy, something we've been working on for the past few years. So in this talk, we'll start off by giving a quick overview of what a muon is, what muon spectroscopy is and why it's important. Then we'll go on to talk about Galaxy, the original platform that inspired the development of Muon Galaxy. And then I'll give a quick tour of Muon Galaxy in the form of a video, and we'll show you some of the features that make it fair. And then finally, we'll outline future work for the project and what we learned developing it. Before that, we'll bit more about us. So the MSCP team is part of the scientific computing department within the Rutherford Appleton Laboratory, RAL. We help to support a lot of scientific facilities on site, one of them being the ICIS neutron and muon source. The ICIS neutron and muon source is one of the world-leading centers in research and in all sorts of scientific disciplines, physical, life, and engineering sciences. We use it to investigate the structures of a wide range of materials and find out its structural and material properties. The ICIS muon source currently channels electron and muon beams to over 30 experiments, and there's approximately 3,000 scientists come every year to test out their materials. But one of the main things that ICIS provides is that it's one of only 4 muon spectroscopy facilities in the world that provide that service. So it is incredibly important to sort of make use of the time, the beam time that it's running for. And our team, the MSCP team, is trying to encourage the use of sustainable, accessible, open source tools in muon science to help and make it available for ICIS and also the wider academic community. But before we go any further, a bit of a physics guest lecture. I'll try and be quick. Muons are basically electrically charged subatomic particles. They have similar properties to electrons, but they have about 207 times the mass. At ICIS, we make a stream of muons that get channeled into beamlines, in which they basically get implanted within a material sample. The implantation site is not random. It is influenced by many factors, but we won't go into detail here. And when the muon is implanted, it stops somewhere within the sample, and over about 2.2 microseconds, it transmutates into positrons, which are then emitted from the material, and then we can detect that using a positron detector. So that bit of diagram there shows muons, which are like essentially all channeled into the material, and then based on the local regions, it'll stop somewhere in the site. That's called the muon stopping site, and then the positron is detected. So one of the main challenges in muon spectroscopy, which is what we're talking about, is where exactly is the stopping site? It could be somewhere within the material. Again, it's not random. It's based on a lot of factors. But we found that simulations can help us narrow the search down, predict potential stopping sites, and then in turn predict material properties based on that. And using simulations, we can essentially improve. It will narrow down experiments needed and make more efficient use of the ICIS beam time. So simulations are becoming more and more important within this field. So we want to try and, our team is building tools for this. And we also want to make sure those tools are available in a available for Muon scientists to use. So some of the tools we've created, PyMuon Suite is one of our main collection. There are command line tools which we use to model physical properties of materials. One of the things we can do with PyMuon Suite is predict the stopping sites, and we'll go through the pipeline of that later on. Another one is MuSpinSim, which is a tool we are currently developing in hopes of simulating spin dynamics, another interesting field for Muon science. And finally, Muon Galaxy, which is our fork of Galaxy, which is to interface between all of our tools, make them available to Muon scientists. So again, here's the pipeline for PyMuon Suite. So a bit complicated, but essentially what we do is we first generate a number of structures. We implant the muon randomly within the structure, and then we perform an optimization step. We do a number of physics stuff, DFT calculations. I won't go into detail, but essentially we optimize the random structures to find potential stopping sites, and then we have to do that multiple times. So we get a nice statistical representation. So maybe like 100 times we duplicate, we create 100 like random muonated structures, and then we optimize them. And then once we do that, we cluster all of our results. And then once we have the cluster, we can then find likely muon stopping sites. And then we can do post-processing steps like using MuSpinSim, using other things. But again, we have to make all this available to Muon scientists, and we can't rely on them using our pipeline, especially for complicated stuff like doing this hundreds of times. So, we don't want them to learn how to use Linux and learn how to use our stuff. So we want to make it available in a nice way. That comes on to Galaxy. So we've outlined the importance of simulations and what they can do for us. So now we have to make them available. So how do we do this in a fair way? And how do we allow the programs that we make, the data that's sort of outputted from the tools, how do we make that available, publishable, how to make it fair? So the Galaxy project is a project that is built for this sort of stuff. It's an open source platform. And here's an overview. So this is a screenshot of Muon Galaxy, but essentially all of the features stay the same. It's a graphical user interface. It's available on our website. So all of these tools on the left are tools that would be made available to scientist users, and they have a nice name. And when you click on them, it's a nice overview of what it is. We have citations at the bottom, and then we have the input. So you can just enter the inputs in. On the right, we have a history. So every time a tool is run, a job is created and it's stored in the tools, stored in history. So we can essentially save everything that we're doing, save the outputs, and then if we want to rerun the program, publish it, make it available for others, we can just rerun that essentially thing. The details of which we'll go into later when we show the demo. So yes, and then we also have workflows. So for instance, for our pipeline, we can create a workflow which essentially goes through all of that stuff instead of manually having to go through each tool and run that. So I'll try to show the demo. Hopefully this works. Yeah. So here's the Galaxy homepage. Yeah, so you can see the number of tools on the left there, and they all have. Sorry, I just want to pause it. Before I go any further. So yeah, so you have the tools on the left here, and then the homepage and history. So currently the history is empty. What we'll do is we'll show you the pipeline for simulating Muon stopping sites. So first thing we're going to do is upload data. You can upload data a number of ways. We're going to do it via our local environment. So we just get tools from our local files. These are files that we use to essentially do the calculating Muon stopping site. One of them is the .cell file, which is essentially a silicon lattice we're trying to do. So once we've uploaded them, they essentially go into the history, which they'll be made available. They'll be saved on our server, on the Galaxy servers. So the first tool here is the generate tool. So we'll provide a structure file, the silicon file, and then we'll provide a YAML file, which details how we generate those muonated structures. Once you provide them, so they're made available when they're uploaded. They'll immediately be available for you to use in the Muon in the tool, and then once you put them in, you can execute. So yeah, it gives you a small description, and then there's citations. So all of that is available, and then once you execute it, a job is created, and for this it's much slower, but for this thing it's a bit faster. Anyway, once it's generated, you can view the job with rich metadata, and including the command line outputs and standard if you have any errors will show up here. Yeah, essentially you can see all of the outputs. So it's just generated a number of structures. Second tool, we're going to optimize it. So from the tool we have muonated structures in a huge zip file. We provide a few other files as input, and finally, after we optimized it, we're going to cluster. So this third tool that we're talking about. Once we cluster, we generate a report, and hopefully you can view the report within Galaxy itself. So one of the things we show here is we've generated about 16 structures-ish, and we found 2 potential stopping sites. First cluster containing this many, and then second cluster containing the rest. So yeah, so about 12 of them clustered around this spot. So that's a potential stopping site, as well as a smaller one over there. Yeah, so that's essentially very easy to use for Muon scientists. They don't have to worry about using command line tools. And then again, we can show workflows. So this is the same thing. It's a workflow which essentially does everything we just said. A nice workflow can be shown. And then we can just run that workflow instead of running any of the tools, providing all of the inputs in at once. But as you can see, the history is made available, and that history, each of those tools can be run again. Yeah, you can see all of them are being queued up, and they'll be running sequentially, one after the other. Yeah, when the final one completes, you can view that, and similar results will be shown. Yeah, exactly. So the final thing I'm going to show in this demonstration is another feature of Galaxy, which is visualizations. One of the things we're trying to implement is a visualization tool for this sort of structure, implementing CRISPR.js within Galaxy. It's a work in progress, but essentially you should be able to see the silicon lattice structure within Galaxy itself, and hopefully in the future we can try to run tools based on interactive visuals just like that. Yeah, so something we need to touch on is Galaxy is very good at reproducibility. Galaxy history stores all of the output files from all running instances, and you can essentially make the history publishable. You can make it publicly available for others to see and verify your work. Each of the jobs is run in its own container, so the prerequisite, the dependencies and the tool versions will all be consistent when you run the same job again. Therefore, it's more reproducible. Each of the jobs have their own unique identification, which means that it's easily searchable and findable. And yeah, each job has a very rich set of metadata. Yeah, which stores all sorts of things like parameter values and job metrics. So moving on, future work for this project is to sort of get feedback on the platform. We've recently made it available. You can also sort of see it on this URL. So if you just go into muongalaxy.stfc.ac.uk, you should be able to play around with it yourself if you're a Muon scientist. But yes, we're trying to get feedback on that and feedback on our tools especially, so we can try and find use cases for to sort of fill. We also, yeah, as we touched on, we want to try and implement visuals into our work, potentially making them interactive and making the tools be able to run off. This is something that Galaxy doesn't currently support. We aim to support it within our fork. Again, something we've not touched on is the Galaxy Training Network. It's a great platform for writing tutorials for tools, and it's something that we need to sort of build for our Muon Galaxy as well. We also want to sort of integrate our tools with high-performance clusters. Lots of our tools require quite a large amounts of computational power to run. So plugging Galaxy to Muon Galaxy to a high-performance cluster would be very useful for both Muon scientists and the running of the tools. So then lessons learned. So being part of the Galaxy community, like originally built for biosciences, it's been very helpful. We've drawn a lot of experience, and it sparked a lot of collaboration. We aim to make Muon Galaxy available. We want to make tools available in Muon Galaxy for material sciences as well, which is something we want to, as we see more collaboration going forward. And we found that working with an established platform like this meant less overhead, more time developing our tools. We also found that Galaxy has quite a few reproducibility features, like we touched on, which encouraged us to sort of make similar improvements to our packages. So regular Conda releases for our tools and usage of containers, CI pipelines like GitHub Actions. It's from like a framework for us to sort of copy and use for our tools. So yeah, I think that's it. Thank you. If you have any questions, let me know. If you want to find out more about the Muon Spectroscopy Computational Project, our website is there. And if you want to contact us about collaborating with us or anything, you can either email me or my colleague Eli Chadwick, who's the team lead.
Thanks, Anish. I think we've got a couple questions on Slido. Okay, so is the Galaxy tool linked to a HPC cluster in the back end? Can you use it on a normal computer? I think you kind of answered that.
Yeah, so the Galaxy is a web platform and we connect it to a backend ourselves. So one of the things you want to do is sort of create like a dummy front end for you to log into, say, a high performance cluster, and then you can use that instead of logging in yourself and running like command line tools within HPC. We make it available for you to log in via Galaxy, and then you can run the tool like that way. Yeah, do you want to answer the next one?
Follow-up question to that: does it execute in reasonable time on a normal computer?
Yeah, I mean, it depends on the use case, right? Because we have lots of tools. Depending on like the size of your like a starting material, it's like our tools. I want to go into detail about the way it's working, but essentially, our tools, we hope that they'll run normally on a normal computer. But again, we connect to a backend, so we have a bit more processing power on that end. Yeah, these tools are run on like a remote server, so not on your computer exactly. But yeah, so the next question: what customizations did you make to Galaxy? Are there any specific use case? Are they specific to use case, or could they be integrated into the main project? So we are making available our tools on the main Galaxy, I believe. There is something called the Galaxy Toolshed, which is a series of collections of tools. We want to make available our tools as a materials Galaxy sort of group. But one of the things we found is that lots of Muon scientists, especially ISIS, might not want to share the data. So we wanted to create our own platform and keep that data separate from Galaxy, which has a number of like collectives. Like there's the EU Galaxies, for instance, and all of that data is made public. So anything you put on there, it's made public. So how up to date is your fork of the main Galaxy repo? Can you install normal Galaxy plugins? I have no idea. I think it's up to date. You have to ask Eli about that. So yeah.
Ooh, a few others are popping up now.
Galaxy looks to be mainly focused on computational biology, genomics. How difficult was it to coerce it to solving physics problems? Actually, the Galaxy tool framework was very simple to use. They make the tools essentially. It was very simple to just connect our command line tools to it. Galaxy framework allows any sort of scripts to be essentially wrapped and put available as a tool. We found it extremely easy to do. Some issues we found were we wanted to put, for instance, a visual on this like tool itself, for instance, so you could see where the muonated structures as they were being created. But that's something that Galaxy doesn't currently handle, and something we want to put into our fork. So that was another something we wanted to do. Do you have to maintain containers for your individual steps? I think so, yes. So each individual step can be rerun individually. So you create individual containers for each step, which makes it more reproducible. But yes, you have to store more data, I guess. Yeah.
Okay, are there any more questions from the room? If not, can we thank Anish and all of our speakers for the morning session?